I'm Dan Burns, joined by my colleague JJ Plank. And what do we got for him here today, JJ?
This is the H over E experiment, right?
So, and Photoelectric effect
right.
is the product name, right?
Mm-hmm.
And that's one of the main experiments, but there's actually a lot of different experiments. We're going to run through the setup, some of the experiments, do some live data collection, show you some example data, and give you a few tips and tricks about this if you have one or a similar system or considering getting one. So we do need to get it set up a little bit, and we've done a little bit already. The mercury lamp is on because you want to warm it up for about 10 minutes, and we didn't have enough stuff to talk for 10 minutes while we waited to warm up.
And it gets hot too, so be careful.
And so there's a track that comes with it as well. So we've already attached the mercury lamp to the track, and then the vacuum photodiode goes on the other end. And if you're reading the instructions, they say to have it about 35 centimeters apart, but most of the setup images show them right on the ends, and that's pretty easy to do, and it works. I wouldn't bother too much about worrying about how far apart they are. But I guess if you didn't have the track, that'd be important to know. And we need to do some connections here. So I have this all unconnected on purpose, except you might notice I have the lower power supply on and a couple of cables coming out. That's because we have that connected to the Frank Hertz tube for our next production here. And so it's kind of like we're a cooking show, and we've got the cake in the oven for the end. And so that's the Frank Hertz apparatus. This is photoelectric experiment. So normally this would be off. These cables wouldn't be here. So we need to connect the current amplifier to the vacuum photodiode. And
you'll notice these power supplies, these stacked power supplies here are used, the same power supplies are used for this experiment as well as other ones,
right,
like the Frank Hertz.
Yeah, both of these, all three of these we'll use for the Frank Hertz.
Right.
And so this is a BNC connector that comes with it, and I've connected it to the current amplifier. And now we can turn that guy on. And there are a couple of things we need to make sure we have ready. There's a range switch here. And on this one, the current is so low that we have it set to 10 to the minus 13 range. So if you're having an issue, that's one of the things to check. Then we want to zero this while we have nothing connected, although that isn't that important because if I push this in, now it sort of disconnects it from the circuitry, and then I can zero it. And you can tell I was playing around with it before we started here, so it's pretty close to zero. But we want to get it right on zero. Should it be positive zero or negative zero, JJ?
Yes.
Although it's positive zero. It's it just went up to 0.01, but it's pretty close. And then key, I've made this mistake before. Get that back out so it can measure current. So if you go up to a setup and the students aren't measuring any current, check that button. It might be pushed in from the calibration. Then we have some DIN connectors to connect to the interface. So whatever interface you're using, this is a PASCO 850. And we need to connect the current. Yeah. It's a slippery table.
Yeah, the glossy surface on the table. You slide around a little bit. Just trying to keep them from sliding.
Okay, we tied this up in a knot.
These power supplies, they stack on top of each other too, and they'll nest like that as well.
But you still got to be careful.
You still got to be careful, yeah.
We're just trying to make some room. If I had a lab table, I'd have each one set by itself.
Right.
So the currents, the way the capstone file we're going to use is configured is measuring here in slot A, but you could pick a different one depending on how you plugged it in. And then we also want to measure we're going to be doing the reverse voltage to stop the electrons and measure that stopping potential. And so I want to make sure I'm measuring this, which is where we're going to be changing the voltage. And that, I have two different connection points here. I want the negative 4.5 to 0.1 here on the bottom. So that's another thing to check. But we have graphics that really help with this. So I'm trying to do it without the graphics. Might be a good idea to bring them up at the end to check. The last connection is to connect the power supply to the vacuum photodiode.
Yeah, that's the voltage. We're gonna create that stopping potential between the anode and cathode, and we'll talk more about that in a second.
So let's, now that I think I have this ready anyway, let's open up the capstone file. And so you can download these now on the website, on the product page for Photoelectric Effect Experiment. And there's a capstone file that students could use. It's all ready for them to go with pictures and questions and directions and places for data collection and analysis in the manual. And also there's a Word file that helps them set that up themselves, at least, you know, the important parts, so you don't have to do that. But let's open up that one.
And then the files that are available online for this experiment, they're editable. So if you want to make a tweak, if you want to change something in the capstone file as well as the Word doc file, it's yours. So feel free to make those changes.
So I brought it up, and you can see it has an image, so most student groups could do these connections for themselves just by going with that image. But there are a few subtle things like this, the selector switch here and there that you want to read the directions for. And it looks to me like we're all set up there. And then there's a page with some predictions. Again, you could change and put in different wording or add some questions.
The workbook file might be locked when you download it. If you just go up to the I think it's the edit menu, there's the ability to unlock the workbook file. Then you can change the stuff on the page.
You say unlock all pages.
Yep.
Yep. And then there's a little bit of theory in here. And so it describes what it is we're looking at. What is the photoelectric effect? What does Planck have to do with it? And they show a quantum well here with an electron.
What does Planck have to do with it?
And so you can see the electron is in a quantum well, and so it needs a certain amount of energy just to get out of the well. If I give it extra energy, then it's got this extra kinetic energy. That's what we're going to be measuring. And that electron looks pretty good, but what if the electron looks pretty sick?
Sick.
It's a quantum unwell. And
it came from an unwell place.
And here we have our some theory continued here, which goes over Einstein's equation and how it relates to the experiment. And you end up with this final equation. We're going to be measuring this voltage. And we have a mercury lamp and 5 different filters that let through just one wavelength. And we can figure out what the frequency is and do a graph of the stopping potential of the voltage versus the frequency. And we get 5 points. And the slope then would be h over e. And so you can figure out Planck's constant in whatever units we're going to do. We'll demo that. Show you a little more of the hardware in a little bit. And also the y-intercept is the work function, but we'll talk more about that, why it's kind of hard to match that with a accepted value. And then there's more about the setup, how we're going to be changing the voltage, zeroing the current thing. Now you might see here it looks like we're not zeroed, but if you want to check it, you can always just push that in and double check that it's still on 0. And it is. And this note in red is in there just for me. No, it's for anybody. When I practice this, I'm sitting in a chair and I'm going to be adjusting this knob. But when I do it standing up, I have a tendency to start adjusting the current knob. And so you don't touch it from now on. We leave that guy alone. And let's And then let's look a little bit more at the hardware here. So the mercury lamp, there's a cover on it.
Which can get hot, so just
the cover usually doesn't get
the cover
too
doesn't get hot, but the housing will
gets
get
warm.
hot.
Yeah. And so you want to keep this cover on when you're not taking measurements. And what I like to do is just put it in a little bit, then it's a lot easier to get off. But I had it in all the way, so it was a little harder. And then over here is the aperture to let in the light. And so there's a lens cover, and even though it's a vacuum photodiode, it's supposed to respond to light. But if you always expose it to light, I guess it wears out sooner. And so having this cover on is good. There's also in the aperture settings, like right now I have it on. It won't fall.
I thought it was falling.
It's on there. And so I'll just try it out. Can you see that on the? So it's set to 4 millimeters, and then you pull it out a little and you can rotate it. There's a 8 millimeter round aperture. That's the diameter.
Yeah.
And then there's a 2 millimeter. So you got 3 different choices. The fourth one is, well, you can turn the filter to 0, and then it doesn't let any light through. So that's what I was going to show. Then there's 5 different filters around here. This one says 365 nanometers, then 405, 436 are all the mercury lines, or 5 bright ones, 546, then up to 577. So we want to start here at 365. And I did test these with our spectrometer, and they're like right on to the precision of the spectrometer. They're within a nanometer of what we're advertising.
Right.
Not that I don't trust our equipment, but any chance I get to use a spectrometer, I'm gonna take it. But you can put it on 0 too. It's another thing that keeps light from getting in, if you wanted that.
Yes.
Now you might be curious about the vacuum photodiode itself, and so this is an older one that I took apart, and you can see what it looks like. It's a glass housing. You might be able to see the anode, which is a little ring of nickel, and then the cathode is the coating on the other side, and the cathode is a mystery material. We have asked the manufacturer, asked a lot of people what it might be. If you have an idea, it's a vacuum photodiode, what that is, I'd be interested. Mainly, you'd want to know maybe what its work function actually is, but there are, again, some reasons why the measurement wouldn't even match it then.
We've found consistent empirical values for the work function.
Yeah.
But to actually know exactly what that cathode is made of, it's not.
And so if you're interested in that, there's a great book, Advanced Experiments in Physics, Melosinos.
Yep.
And we'll put a link to that in the chat. If you don't have a copy of that, I'd recommend it. I kept borrowing Ann Hank's version, and it really helps understand what's going on with this equipment. So let's go to the first experiment. And again, this file is kind of all set up for the students. You may or may not want to do that. My approach typically was earlier in the year, the files would be set up more for the students. And as the year went, I'd have them do more and more. But, they're probably in college doing this, not even probably freshmen. And so they probably can handle setting up this. But it's good to have something they can use if they need it. And we have the wavelength here and then the frequency. How did the frequency get there? Well, if we go over here to the calculator, you can see right. I guess they just typed it in. They didn't put an equation.
Right.
So you could put an equation in for it. But there are some constants in there for helping. And then we've set the current reading.
So
it's times 10 to the 14th.
Right. What Dan's referring to is the students are going to be reading the nanometer wavelength value off of the filter, right? And they could, if they want, enter that into a table in Capstone, and the Capstone calculator could use a calculation to process that value and
using the speed of light,
output the frequency. Yeah.
Later, we're going to do an experiment to get the speed of light,
Yes.
so they can go and find that.
Yeah.
So what we need to do is down here, you notice it says preview. We're in sample mode. And so if I click on that, we see, hopefully we see voltage. Yeah, I think we're getting it here. We see the voltage and the current that we're currently reading displayed in the data table. And if I like that, all I do is click on keep sample, it'll save it in the data table, and then I can move on to the next filter. So let's do this first one. That's 365 nanometers.
So I'm going to pull the shroud off, and so we're going to have light exposing the cathode on that vacuum photodiode.
So, I'm not down here looking into the lights.
Right.
So I think we're okay, but I think in a lab setup, I take some care to make sure that was not pointing in a place where somebody be looking into it frequently. You get cataracts, I guess. And
yeah, there's UV coming from that mercury source, and it can be dangerous, so we don't want to look at it. Yeah.
So the current reading is off the scale here. Oh, I did what I said I wasn't going to do.
You turned the wrong one?
Yeah. Just as an example of what not to do. I can get it back.
Yeah.
Here we go. And so I need to put a stopping potential on to try and stop the electrons with the most kinetic energy, right? There's a spread of them.
Yeah, so that light is incident on the cathode, and electrons are being ejected with some energy. Some of them have more than others, right? The potential well they sit in might be a little bit deeper, but the maximum kinetic energy, we want to try to match that to whatever that stopping.
You want to stop them all.
Right.
Got to stop them all.
I have a question.
Question?
Yes. Says is the decimal place of the wavelength from the filter label or from looking up the mercury spectrum?
The filter label does not have that decimal on there, so I would guess somebody looked it up and put it in the data table.
You could also, as Dan said, use a spectrometer, right? So the housing comes off and you can put a fiber optic in there to look at what comes through the filter. So you can measure directly what the wavelength value is.
Or the experiment yesterday we did with the
student spectrum photometer, right?
So these all connect.
Yeah.
So that's pretty close. I'm seeing a current really close to zero there. And so I'm just going to say keep sample. And so that's the stopping voltage for the first wavelength. And once they do one, the others go pretty quickly. I think I'm just going to go to the longest one. We'll get two, which I would never do in class, right? I always want as many points as possible, but in the interest of time. So JJ has that on the 577. So I'll move down to there, but normally, again, you wouldn't do that. We'll do some of the others in the other data collection. And you can see now I've got negative current. So I'm not only stopping the electrons, but I'm sending them back the other way, right? So I need to lower the stopping potential. So these will be the least energetic with the longest wavelength.
Right. That KE max is the smallest.
But they're all long enough to eject some electrons. There's none below the stopping potential. So that's pretty close, zero. And so I say keep sample. And again, normally you'd have 5 points. Now I can stop data collection and go up here to our graph. And I've got 2 points. And if we do a linear fit, I guess the slope is negative 0.408. And if you convert that to EV second units,
right.
that's the easiest, right? It'd be 4.08 times 10 to the minus 15th. And notice he has to check me here because he's an expert on Planck's constant. And the actual is 4.136.
Yeah,
that's a pretty low percent error. Now I'm using the 4 millimeter aperture. You might get slightly different precision with the others, and so that's kind of a good thing to do. Have one group do the 2 millimeter, one group do the 4, one do the 8. I found the 8 with this particular tube didn't work as well.
Right.
And it could be it's shining on a greater part of the vacuum photodiode on the cathode.
Right.
And it's not as uniform. Or
yeah, that's because the theory would state that we should see about the same curve, and the same values, but I think you're right. I think maybe the aperture is wide enough to where it's exposing more of the cathode, and there might be areas on the fringe of the cathode that aren't quite as uniform in terms of the composition of the material.
But the equipment works well enough so that the concept that the intensity isn't going to change the kinetic energy of the electrons works really well, and that's the next part to this. We have a light intensity experiment where we just get 3 different points. This one has us do it at the 436 aperture, so you want to put that to 2 millimeter and then 436. And notice how he's being safe by putting the cover on.
I'm getting a tan over here.
Yeah. And so this, I'm getting some current here. Makes sense that I have to have a larger stopping potential because we just shortened the wavelength from the 577. So it takes this guy's got a little lag to it, so you wait, and then that's pretty good. So that's negative 1.115. And then now we just keep the same wavelength, but go to the 4 millimeter aperture. And if the theory's right, I shouldn't have to change the stopping potential to keep the current at 0.
436, right?
Yep. Worked a little better yesterday. Going down. And so let's see how much I do have to change. And now it's negative 1.19. Yesterday I didn't even have to move them. I wonder what. But still pretty close. And then the 8. And this one was a little different yesterday. Shouldn't matter. I don't think the earthquake affected this experiment.
Yeah, we experienced a bit of an earthquake, and epicenter was in one of our neighboring towns up near the Sierra, and affected some of our precision alignment in our experiments.
But here we have the results. So if I double the aperture, I'm increasing the intensity. If you go by the area, right, by 4.
Right. Yep.
And the stopping potential just went up a tiny bit. And then I've tripled it going up to 8, and it's got virtually the same stopping potential. So the concept, I think, is still something they can pull out of that. This last one takes a little bit of time to measure the data. I think we will maybe start on this one, and then we'll show you some results. So what I'm going to do now is not just turn it to the stopping potential, but keep going and go positive.
Yep.
And we're just going to measure the current as we go. So let's turn this guy. So we're going to change the range now. So I'm going from -4.5 to 30. So I go all the way there. And let's see if that's still zeroed, so that's still pretty good on our measurement there. I haven't touched that knob. I only did it once, right? Changing the current knob. So this also is a showing something here. Oh, we want it on for this one. Want it on 436 and
4 or 8.
You can put on any of those.
Okay.
They do all three. We're obviously
Right.
What do you got on?
It's on
4?
8 right now.
Okay. Guys on. Oh, I know. And we changed the range.
Can't see that side.
Yeah, you would. JJ would have caught that. Minus that should work. So now I click keep sample. And I just turn this a little bit, give it a chance to settle down a little bit, and keep sample. And I just keep going all the way up to 30 volts. Now, to me, the important part is close to the start here. So I would take a lot more points now, and then I can go faster.
Yeah, because it doesn't change a whole lot.
But you get a visual of the current staying 0. Essentially 0. And then it starts to go up.
Yep.
And once it starts to go up, I start turning it a lot more, like maybe give it a whole volt or so. And so you keep doing that, and then you can do it for each aperture.
Right.
There's an additional experiment in the manual where they would do this for 3 different wavelengths as well, to look at the current versus voltage graph for different apertures, same wavelength, same aperture, different wavelengths.
Right.
But that one isn't in the capstone file. So let's open up the one with the data. So you'll see there's a file that says photoelectric effect with data. And so all the files, all the pages are the same, except it's got answers. And so this one you probably wouldn't want to hand out to the students until after they've turned their lab in. So if I go here, you can see there's a graph with all the points. It also shows up on the analysis page. It's got the slope. They've got -4.06. I think we did a little better, which is 2 points. So that's bad. We don't want the students to know that. But I'm sure the standard deviation is better. And it has the questions, and then down here are sample answers. And some analysis. And they do talk about the y-intercept here, which I always got it coming out to about 1.5 volts. And so that theoretically is the stopping voltage, but you have
work function.
Work function.
Right.
But you have things that are interfering with that. We're stopping the most energetic electron. They have a spread of energies. There's a field effect. So as they're coming off the cathode, the ones that come later are interfered with by the negative charge electrons that are still nearby. And the contact potential, if you read the Melosinos book, actually, if you work it out, the work function should be closer to the anode's
Right.
Work function.
Because of that the concept of contact potential.
But it isn't because of these other factors. And I'm not sure if this happens with our device, but on some of them, the cathode material over time can deposit on the anode.
Right.
But you might think, why not get a piece of zinc? What do you got to do to zinc to do this? You gotta polish it, right? And so this, no polishing needed. And so there's a similar light intensity experiment. That one worked out a little better, but we did that one. There's a full curve for doing 2 of the apertures. And then you could also do do it for different wavelengths that isn't in this capstone file. And again, there's answers to the questions. If you remember, we did predictions at the beginning. Now they revisit those. So you could definitely have students do this lab with the capstone file that have not read about the photoelectric effect yet.
Right.
And they would learn a lot from the experience. And then you might be wondering, well, if I can't check the work function, well, let's see, that's for a different thing. So no, I put that in the wrong file. So I think we have given you a good overview of all the things this can do. Are there any questions we didn't get to, Janet?
Nope.
Nope, we answered them all. That's either good or bad. I'll assume it's good. And so we're gonna do a little bit of setup for the famous Frank Hertz experiment next.